This meeting is being recorded.
In this next video from chapter 15 on chemical equilibrium, we'll take a look here at sample exercise 11. We're told that we have a reaction that is allowed to reach equilibrium, and we're given some initial pressure values. So we have CO at 2.0 atmospheres. We also have H2O's initial pressure over here of 2.0 atmospheres, and we're given a Kp value of 23.2. So with that information, we're asked to determine all of the equilibrium pressures. So we're only given initial pressures, so we know that we're going to have to set up an ICE table here to incorporate the initial values, any change that occurs, and then solve for our equilibrium values. So let's take a look here at how we can begin this process. So we're told that the initial pressures rather for CO and H2 are 2.0 atmospheres each. So we'll plug those in. And if we're not told anything about reactants in this case, we can assume that 0 of that has been allowed to start the reaction. So we have no initial pressure for CO2 or H2 gas. So knowing the stoichiometry of this reaction is all 1 to 1 to 1 to 1, we know that as this goes down with a 1x coefficient there of 1, these would go up by the same amount. And now we just add together each of these two rows, so we get 2 minus x here, 2.0 minus x, and then again 2.0 minus x equilibrium, and then these are just x and x. Now you're probably thinking that's a lot of variables. How can we possibly solve this? Well, we're given Kp, and we're told that that value is 23.2, and we can set up our equilibrium expression with products here. So that would just be x squared over. We're going to do the same on the bottom and square 2.0 because this times this, the same value. We can do that. Now, we can take a shortcut with this specific product, or this specific problem, because we see that we have both squares on the right-hand side of our equation here. So if we take the square root of 23.2 and set that equal to the square root of x squared over 2.0 minus x squared, we end up with a simplified equation that Kp would then equal x over 2 minus x, and that will be equal to the square of 23.2, so that's 4.82. All right, so now we can move along here and figure out how to solve for x. So let's see if we rearrange this equation, we'll end up multiplying over here by 2 minus x. We'll distribute these values here. So we get now x equals 9.64 minus 4.82. Oh, 82, not 28. X. And we can keep going. We can combine like terms here, and we can see that we can subtract or rather add 4.82x to each side. So I'm going to bring this equation up here. So now I see that I have 5.82x equals 9.64. I'm going to divide both sides by 5.82. I'm going to get my x by itself. And 9.64 divided by 5.82, we get an x value approximately 1.65. So we're almost there. Now we just need to make our final plug-ins here. So we're going to do 2.0 minus 1.65 for each of the CO and H2O concentrations. So again, we just plug in 2.0 minus 1.65. So that gives us our equilibrium concentrations for these of about 0.35. Then we have our CO2 and our H2 concentrations. Those are both X. So we know that those are equal to one another, and they're also just equal to 1.65.